Hi guys. So today we're doing a new chapter, which is work, energy, and power. Right. So we're doing work, energy, and power, which is also quite interesting a lot because when people think about work, they think about going to work and just a job. They think about a job. But in physics, when you talk about a work, we don't necessarily mean a job. So today we're gonna be diving into work and energy and then power. So this is just an introduction video to all of the concepts and stuff, and we're gonna have more practice videos like we usually do, right? So let's begin. I want to start here with the word work. What is work and how do we define it in physics? So work itself, right, has a bunch of properties, of which the first one being work is the transfer of energy, right? The transfer of energy. I'm not gonna write everything down. By the way, I'm just gonna say some stuff to save some time. And that work done on an object, right, is the product of the displacement and the component of the force parallel to the displacement, right? And the last one being um, the definition of work. Those are the three properties of work. But then I want us to start with this one, the transfer of energy. Remember, when you do work, you're basically transferring your energy onto the object or whatever that you are applying. Let's say, for instance, I'm pushing a large crate. This is a large crate, right? I'm pushing a large crate. Since I'm pushing a large crate, I'm transferring my energy onto this crate in order for it to what? To move in the direction that I want it to move in, right? So that's what they mean. And the second statement that said work done on an object by force is the product of the displacement and the component of the force parallel to the displacement. It's just what I have drawn here. So it is stating that work itself, it's the product of what? Of the displacement and the component of the force. That's all they're saying. That work is just the product of the displacement and the component of the force parallel to the displacement, parallel to the surface. That's work, right? So that's all I can say about these two properties. And then the last one being the definition of work, of which work it's defined as follows in terms of an equation. This is the equation of work, right? Right. This is the work formula, right? So it's important for you to know it, right? And what each and every variable stands for. So F basically it's the force or the magnitude of the force. Change in X, it's the displacement that we were talking about. And the cos or the theta, let me just focus on the theta because cos we know it's just cosine, it's a trig ratio. The theta is the angle between the force and the displacement, right? Between the force and change in X, right? It's just the angle between the two. And one thing to note is this: unlike the other chapters, momentum, vertical projectile, work itself is a scalar quantity, meaning it doesn't have a direction, it only has a magnitude. And the unit of work is joule, right? So, yeah, this is all I can say for the work part. And please know this before we move forward. Work always involves two things, which is the force which acts on a certain object, which is the F, and the displacement of that object, which is the change in x. So that is basically important, right? That is basically important for us to know about those two things. Now, I want us to talk more about the types of work. Now, we have two types of work. We have the zero work, positive work, negative work. What do those things mean? Right? So let me try and write them down here. So when we say zero work, what are we trying to say? So zero work basically it means no work. No work is done on the object. Nothing, zero. There's nothing. No force. If there's no force, there's no change in x, and yeah, nothing. Nothing is happening when we say zero work, right? So there's no work done on the object at the constant velocity. Like there's nothing that is happening when we say zero work. And when we talk about positive work, it's when the force increases the energy of the object, right? So basically, it's when the object is moving in the positive direction. That's when, yeah, that's when the work becomes positive. And negative work, this one, it's when the force component or the force is in the opposite direction, right? Causing the object to move in to do what a negative work. So yeah, basically these two um, concepts are based off the force component. So if the force component is not moving in the positive direction, we consider the work to be negative. Why? Because if the F is negative, remember that work is F changing x cos theta. If the F is negative, then the whole thing is what? It's negative, right? So it's important for it um to be positive or negative, right? Yeah. Right now, let's move on to other things, um, such as the work net, underwork, right? Network, right? Not network of the cellular phone thing. Network on an object. Let's talk about that. Now, a network basically, like we have been doing, it's the addition of all of the work acting on the object at the same time. Now, each force can do work in the same direction, and some may not even be in the same direction, right? So, yeah, that's one thing. And if the network is positive, energy is added. This is important. Energy is added to the system. Now, this is not what this is. Let me write it well. The network, if it's positive, energy is added to the system. Now, if the network is negative, energy is removed from the system, right? So it's important for you to know and differentiate when the work net, the total sum of all of the work acting on the object. If it's positive, this means this. If it's negative, this means that, right? So yeah. Now we're going to be moving to another part of which is it's the what's this? It's the work energy theorem, right? Just after I've done, I have erased some of the things here, right? Right. Now let's come here. This thing quickly. Now let's come here and talk about work energy theorem. Now the work energy theorem, what does it suggest? Basically, the work energy theorem, work energy theorem, what does it suggest, or what does it mean? What is the definition? The work energy theorem, or the network as many people like to say, is defined as follows. It's the network done on an object that is equal to the change in the object's kinetic energy. Now, in simple sense, you can just look at the formula and just say, oh, work energy theorem is the total work done on an object that is equal to the change in kinetic energy. And you're done. You don't need to do much. You just have to know that the work energy, um, its formula is this, and the definition is the one that I just stated, right? Now, the work energy can be applied to objects on horizontal, vertical, and inclined planes, right? For both frictionless and rough surfaces. It's not limited, right? It is not limited, so it's important to know that. Right, now, here are the formulas, some of the formulas that are going to be used in work energy. Right, some of the formulas that are going to be used in work energy and power. Actually, let me just let me wrap up everything here, and I'll put the formulas at the end, right? Yeah, I'll put the formulas at the end. Now, there are two types of forces that we have in work. Types of forces. Now, we've got conservative forces, conservative forces, and non-conservative forces. Now, these two forces are basically different. They're not related to each other. They're just different in their unique way. Here's why. Conservative forces, right, is the force for which the work done, right, on a moving object is between 2 points and is independent of the path taken, right? The keyword, it's independent. It does not depend on the path taken, the displacement taken. It doesn't depend on that. Dependent. And this means the non-conservative, it's going to be the opposite. This means this one is what? It's dependent. Now, let me read out the definition, or tell you the definition. The definition is a force for which the work done on a moving object is between 2 points and is independent of the path taken. Right? That's one thing you need to know. Now, examples are as follows. Right? Types of conservative forces. The one that is mostly popular: gravity, gravitational force, gravitational force. Right? This one is mostly popular. Right? The second one, elastic force. Elastic force in a spring. Hooke's law, for those who don't know, it's a spring. It's a force that exists in a spring. That when you try to, let's see, when you try to compress a string, it always goes back to its original position. Yeah, it's independent of its path. It will always act in its direction, right? Then the other one is electrostatic forces. Now, even this one's conservative forces. Now let's come to the non-conservative forces. The non-conservative forces are the type of force of which the work done on a moving object is between 2 points and is dependent on the what? On the path taken. This one is dependent on the path taken, and the example being what? Frictional force. This is frictional force, air resistance, right? Air resistance, tension, etc. Right. So it's important to know this. Let me say tension. It's important to know the difference between these two because you are going to find scenarios whereby you need to calculate the network, and in that case, if you have a non-conservative force, you're gonna use this formula here. You're gonna use this one. Now this stands for potential energy, change in potential energy plus the change in kinetic energy, the work done by the non-conservative force. Maybe you'd find that the object it's sliding down a ramp on its own. This means is what there's friction. So friction is the one that you're going to substitute here, right? Air resistance we usually avoid it. We don't usually use it, but then yeah, it's not a case of maybe one day waking up and finding that we are calculating air resistance. That's gonna be quite interesting though. So yeah, those are the two things you have to know about these two forces. And let's move to the next part. Let's see. Let's see this one here. Right. All right. Now energy. Now energy is going to be quite short. I won't take much time on this one. We already know this one, the principle of conservation of mechanical energy. That's the one that we're talking about, which states that the total mechanical energy in an isolated system remains constant. So yeah, that's the only thing you have to know when it comes to energy, right? So when it comes to energy, it's just you have to know that we also include mechanical energy. Like in that formula of the non-conservative force, it's equals to the change in potential energy plus the change in kinetic energy, right? So you just have to know that okay, these two are not two different things. It's mechanical energy, right? Good. Now, power. Power. We're just gonna do the formula, of which the formula of power it's written as P is equals to work of change in T. Now you may be asked to find the work, and then after that, come and find the power, and yeah. So this is where I'm gonna end off this lesson, and yeah, I'm gonna end it off here. And as I said, I'm gonna show you the formulas, right? Before I forget, there's one thing we have to note about power, which is the average power. Average power, should write. Let me just write it. Well, I shouldn't be doing this. Average power it's the one that consists of the what? Constant velocity, right? Constant velocity. Sorry for my bad handwriting. Now the formula for it involves P average. It's equals to FV average, right? This is velocity, the average velocity, and this is the force. How can you find the average velocity? Like you've always been doing, the formula doesn't change, right? So when you're asked to calculate average power, you just use this formula. Now, going to what I promised, I said I'm gonna write down all of the formulas that you use in work, energy, and power, but then some of them will be given in the exam. I'm just gonna write down the important ones right now. The ones that you're going to use a lot. I think I'm just gonna write two of them. So the first one being work, it's equals to the force changing x and cos theta. Now for this part, don't stress on the angle. The only thing you need to know is with the two angles that we're going to use, it's the 0 or the 180. Some cases I don't know if they may use 90, but yeah, usually we use 0 and 180. 0 being the positive, 180 being the negative. So if it's a frictional force, you're just gonna write 180. If it's a normal force, maybe a pushing force or something, not the normal force, a pushing force, you're gonna write 0. So yeah, let's see the second one being this one, the one that I wrote. This one is also important. It's so important because you're going to apply it, right? So, and the p average of which the one that I've written. Yeah, I'm just gonna end it off right here on the two formulas. So these are the two formulas that you're going to use a lot in this chapter, and I hope that you understood. Uh, yeah. So guys, I'll see you in the next couple of videos that we're going to have, and I hope that you understood. If you didn't understand anything, please leave a comment below, and I'll respond to you as quickly as possible. Or you can send an email to a message to my email, right? Just like that, guys. I'll see you in the next one.